We're going to continue on the air pollution control methods. And starting from this class, we're going to learn more detailed particle control devices. Okay, so we have been learning about the single particle dynamics, right? The drag force, how the particle move under different force fields, right? And basically their transient movement under the gravity or under other forces. So starting from this class, we're going to start to learn more detailed, more practical particle control devices. So the first one we're going to learn is gravitational settler. People also call this as the settling chamber, all right? I think this is a very basic start because we have been learning about the gravity settling movement of the particles. So just doing a quick recap, right? So we have been talking about the different types of drag force, right? So we have different types of expressions. We basically have the Newton's form and also the Stokes form. I think the Stokes form. Okay, so if we do this quiz again, so I have been telling that we need to memorize what is the expression for the drag force. Again, let's do that. Okay. If you still can't memorize it for now, try to refer to your class notes for the previous classes. Okay, 5 more seconds. All right, we'll stop here. Okay, so I think almost all of you have a good understanding of the drag force now. Okay, so it's the second option. That's 3 pi mu dp multiplied by VR. You know, VR is the relative velocity, right? And divided by c. The c is the Cunningham factor, right? The Cunningham factor is further dependent on how large the particle size is, right? And also the mean free path. Okay. So this is the equation. We're going to use that again in this class. So then we looked at a few steady state problems. So we introduced the concept of the terminal velocity. So the way we solve that is by equating the drag force with the gravity, 3 pi mu dp VR divided by c, right? So based on this equation, we can calculate what is the VR. So if I remember it correctly, that's going to be 18 mu dp squared rho p g multiplied by c, okay? So this is the settling velocity of the particle. And this is under the steady state, okay? So we also have the transient, basically the transient form, which is the time-dependent form. So this is the equation that we went through during our last class. So basically we want to understand what happens before a particle reach to its steady state, right? Because at the beginning, our particle only have the vertical or the gravity force. As they start to move, we're starting to have the drag force. The drag force is going to increase as a function of time, and finally it's going to reach to a steady state, right? We try to understand what is the transient movement of the particles. So we further introduced a term that's called characteristic time. So basically for very small particles, it's going to reach to steady state very quickly. So we introduce a time is almost 10 to the negative 5 seconds. So as soon as it's introduced to the flow, it's going to reach to steady state. But if we have a very large particle, relatively large particle, 1 millimeter particle, then it's going to take 10 seconds, right, to reach to steady state. So basically, particles with different sizes, they're going to settle or they're going to move very different. And at the end of last class, we briefly talked about all the different types of the particle removal devices. Okay, so we mentioned that there is a settling chamber or gravity settler. Right, we have cyclones, ESP, basically the electrostatic precipitator. Right, and then we have the backhouse filters, and so on. So in this class, we're going to start with the gravity settler. Okay. So people also call this gravity settler as the settling chamber. Okay, so you can think of it as as a system that looks like this. So let's imagine that we have a room or we have a chamber. Okay, it's of a cube size. Call this as the settling chamber. So this chamber is filled with particles. So it's similar to our room, right? We introduced that the indoor concentration of the particles is around a few thousand particles, right? So there are quite a lot of particles in this chamber here. Okay, so let's assume that the chamber has a height of h and a base area of s. Okay, the base area is s. And this is at time equal to 0, okay? So as time progresses, then what we know is that all of these particles, because of the gravity, they're going to settle down, right? And then a lot of these particles will basically settle to the base of the chamber and never come back, right? So let's say what happens is after a certain period of time, if we imagine what's happening in the box, then we're going to see like an imaginary boundary here, where above that there's no particles, but below that we can see these particles. Right, this is at time equal to, let's say, t1, or say time equal to t. That's going to be a little bit easier to express the equations. Okay, so time equal to t, we have particles settling down to this height here. Okay, then let's discuss what is the removal efficiency. So removal efficiency is basically the amount of particle that's removed divided by the initial amount of the particles, right? So there's this eta term here called removal efficiency. All right, so for this problem, if we want to consider the removal efficiency, it's just the particles that's existing in this volume divided by the total volume, right? The removal efficiency, because after all, it's these particles being removed. So the particles that's originally existing in this volume basically got settled down to the base, right? So what happens is we can quite conveniently express this removal efficiency. That's going to be Vt multiplied by S, which is the volume of this space here, right? We multiply that by the concentration and then divide by the original concentration, which is H multiplied by S multiplied by C. Right? C here is the concentration of the particle. right? So for this equation, you can see that quite many terms can get canceled out. C got canceled, S got canceled, right? Finally, we just have VT divided by H. Okay, so this is the particle removal efficiency in this settling chamber. It's related with the vertical velocity or the settling velocity of the particle, right? It's related to how much time we have given it to this system and related to the height of this chamber here, right? So then how do we calculate this V here? V is the terminal velocity. So what we can do is we can equate the gravity with the drag force, right? Again, the drag force is 3 pi mu dp divided by c multiplied by VR. VR is basically the relative velocity or just as a settling velocity, right? So we can use this equation to derive what is the vertical velocity of the particles. And then we can just plug that in to get the removal efficiency. Any questions until now? Good. So if no questions, can you show a thumb up, right? Really want you to understand this process. Okay, great. If you use a camera, you can also do that. All right. So, okay, nice. So I hope this is straightforward enough. All right. So one thing that we have been assuming in solving this problem is that we assume that basically there's no mixing of the air, right? Because we know that once the air can mix, let's say if we have a fan, then the particles will also get suspended up, right? So that's going to be a little bit more complicated problem. We're going to talk about that later, right? And the second thing is that we assume that all the particles have the same size. Right? Because right now, we just solved for this settling velocity by assuming that particles have the size of dp. But particles with different sizes, they're going to have different settling velocity. And we cannot use this equation directly to solve that. So, I mean, you can always derive it later, but here I'll just show you the final answer here. So that's going to be dp, it's going to be lowercase d, dp squared, rho p g c multiplied by t divided by 18 mu h. Okay, so basically you just calculate what is the settling velocity. We mentioned the settling velocity is dp squared rho p g c divided by 18 mu, right? So we plug this in to get this final equation here. All right. So this is the complete form of this settling chamber problem. When we calculate the removal efficiency, when assuming there is no mixing of air and also all the particles have the same size of dp, then we can use this equation to calculate the removal efficiency. But so let's say we try to plot out this removal efficiency, okay, as a function of time. So we know that since it seems that it's quite linear, it's actually linear to time, so it's going to increase. But we know that it's not going to increase indefinitely, right? It has to reach to a certain value, and that is 1. So this removal efficiency cannot reach above 1 because there's just limited amount of particles in the system. And once the particles at the top of the chamber settle down to the ground, then there's no more particles, right? So that's why it's going to follow this line here after a certain time. Okay, so theoretically, if we want to represent this removal efficiency, then it's going to be a piecewise linear equation, which is dp squared rho p c or rho p g c t divided by 18 mu h, when V multiplied by T smaller than H, okay? And that's going to be and when Vt is larger or equal to H, then the removal efficiency is going to be 1. It's not going to increase further up, right? So here we're assuming that there's no mixing of air and all the particles have the same size. So what about we remove this first assumption, okay? So now we have a system, let's say have a fan at the top, right? And then it's again filled with particles. So now we know that actually the particles settling down are those that's at the base, right? So because of after a certain time, the particles are going to settle down for a certain amount of distance, and once they've hit to the ground, then they're basically removed. But all the remaining particles can still get suspended up to the top, okay? So we can basically use another mass balance to look at this problem. So the way we can do that is, let's assume that there's no need to make any assumption, but let's just calculate what is the change rate of the particles in the system. Okay, so basically we have Hs, right? So we still have H multiplied by S. This is the volume of the chamber, and then if we multiply by dc, which is the change of the concentration that's in the chamber, and we know that it's caused by the settling of the particle that's at the base of the chamber, right? So that's going to be V dt multiplied by S multiplied by C. Right, does that make sense? So V multiplied by dt is this very short distance, V dt. And then to calculate what is the amount of particles getting removed, we have to calculate first what is the volume of this base plate, right? So that's going to be V dt multiplied by S, right? And then the concentration within this very thin plate is C. So basically during a time of a dt, then this amount of particles are deposited, this amount of particles are removed. And then in terms of the whole system, this is a change rate of the particles in the chamber, right? So with this equation, we can again cancel a few terms. So S can get canceled, right? And then we have dc dt equal to minus V divided by H C V divided by H multiplied by C. Because dt got moved here, right? Dt got moved to the left-hand side, and this is what we get. Okay, so we have a differential equation. So instead of having this linear relationship, now we have a differential equation, and this is quite straightforward to solve. We have C equal to C0 exponential minus V divided by H multiplied by T. Okay. So if we basically plot out what is the concentration or what is the removal efficiency, then we have something that looks like this. Okay, so this is a particle concentration. It's going to decrease exponentially, right? With the concentration, we can calculate what is the particle removal efficiency. That's going to be basically 1 minus C divided by C0, right? So the amount that's being removed is reciprocal to the amount of particles that's still remaining in the system. So this is a new removal efficiency, okay? But in general, in industry, we're not going to use this large mixer here. So, so for the next few examples, we're just going to look at this problem, okay? So we still assume that there's no mixing of air, and maybe particles will have a few more different sizes, okay? So now let's continue our assumption that there's no mixing. Okay. So here you can see that for this problem, right here, we're assuming that the particles only have one single size, right? So what happens if we have particles of two different sizes? Okay, because we know that in industry, when the combustion, let's say the fossil fuel combustion or coal-fired power plant, when they generate particles, it never generate particle of a single size. It's going to generate a spread of particles. Okay, so let's start from the second step. Let's assume that the particles have two different sizes. Okay, we have dp1, dp2, and let's assume that the concentration of the particles in the beginning are C1 and C2. Okay, basically we're assuming something that's like this. Okay, we have two different sizes. Let's assume that this fraction here have a particle size of 1 micrometer, and this fraction here have the size of 2 micrometers. Okay, so we're assuming that there's a separation of the particle size. So it is actually still quite straightforward to solve for this particle removal efficiency. It's just basically we're imposing another fraction of particles. Let's use another color here. So they're going to settle with a different velocity, right? So while this original dp1 might settle for this long, the other fraction might settle for a longer distance or a short distance. So with this new distance, we can calculate the filtration efficiency or the removal efficiency. So if we use the expression to show it out, so that's going to be eta equal to m1, not m1, c1 multiply eta 1 plus c2 eta 2 divided by c1 plus c2. Okay, so again, the removal efficiency is the amount that's being removed divided by the original amount. Okay, C1 plus C2 is the original amount. We cannot directly use eta 1 plus eta 2, right? So this is not correct. We need to consider what is being removed in the system divided by what is the original amount of particles. Okay. And in terms of eta 1 and eta 2, they still have this this original relationship, which is basically eta equal to Vt divided by h, right? We just need to plug in eta 1 equal to V1 T divided by h, and eta 2 equal to V2 T divided by h. So basically, we're going to have C1 V1 T plus C2 V2 T divided by C1 plus C2 multiplied by h. Okay. So basically, you can see that we can further take the time term out, right? So both of the terms in the denominator have the time in there, and in the denominator we have the h in here, right? So this is for two different sizes, right? What about when we have n different sizes? So it's similar to the two different particle sizes. We just need to add in more terms, right? So the eta is going to be, let's say we take the time term out, and we have Ci multiplied by Vi. I can be 1 until n, right? In the denominator, we have h. It's going to be the sum of I equal to 1 until n. So does this make sense? Right? When I equal to 1, this is what we get in the first equation here. It's just Vt divided by h, mainly because the c term here got canceled. Okay? And when n equal to 2, you can see that it's actually just this equation here, n equal to 2. And when n equals to infinity, basically we can just plug in particles with different concentration and also particles with different settling velocity. So again, this Vi here is the settling velocity of the particles with the size of dpi, right? We can use the mg equal to 3 pi mu dpi multiplied by Vr divided by c to calculate what is the dpi. So you can plug that in. Okay. Any questions? No questions, sum up? If you have questions, you can just type in the chat. Okay, I want you to basically learn this process, and you're going to have a few homework problems on this. All right. So for those who haven't showed the sum up, so should I just introduce this again? I think we should be good. So if you have any questions, you can also ask your classmates. Okay. Let's see some chats here. Yeah, so I saw the questions about the previous lectures. So I'll post those. I'm still processing them. I think I can get that done this afternoon, right? Okay, so right here we were assuming that particles having n different sizes. Okay, so you can think of it as a situation that looks like this. So we have dp, we have concentration, right? They can have this basically a size distribution. It's similar to the impactor measurements, right? At specific size, we have specific concentration. But we also mentioned that for real size distributions, it's never this discrete form, in this discrete form. They're going to be in the continuous form, right? So if we have a continuous form of the particle size distribution, we're going to basically convert this summation here into an integral, right? So this new removal efficiency is just going to be an integral of the dpi. Okay. So I shouldn't show this I term here anymore because the particle size is already a continuous form. Okay, so that's going to be particle settling velocity multiplied by the concentration of the particles. And then we take the integral. Okay, same for the denominator. We're not going to have the I anymore. It's going to be a continuous form. Okay, so again, this V dp here, we should solve that with this by equating the drag force with the gravity to solve for the settling velocity. So this is how we calculate the removal efficiency of a settling chamber for particles with continuous size distributions. Okay. All right. So actually, in industry, people are never going to build a chamber to remove the particles. Think about that situation. So one thing is for coal combustion or for other industrial devices, we're generating these polluted air all the time, right? We cannot, let's say, accumulate the time for 1 hour, send it into a room or chamber, let it settle down, and then release that. So we always have to process these flue gas in a continuous form. So that's why we're not going to have these cube-shaped chambers. Instead, we can just use the duct. We can just use the duct to remove the particles in the flue gas, right? Because we always need to transport the flue gas into another location. So for example, for the coal-fired power plant, once the particles are getting emitted, it has to go through all different particle removal devices and finally sent to the stack, right? So while the particles are being transported to other locations, inside the duct, they can get removed, right? So let's say at the inlet, we have particles with a pretty high concentration. And then as they are being transported to another location, let's assume that the length of the duct is L, right? The height of the duct is H. While they're being transported, the particles, some particles can get settled down to the ground, right? Or the base of the duct. And then at the end, if we take a slice, particles will basically get contained at a lower height here, mainly because the larger particles got settled down, and then these remaining particles will settle down for a distance as well, right? So under this situation, we can also calculate its particle removal efficiency. So what we can do is we can just follow one slice of the volume, right? So we know that this slice of the volume always moves forward or along the flue gas, right? Let's say at the middle, this thin slice here got settled down for quite a short distance, right? And at the end, they can settle down for a longer distance. So basically, we can still calculate its removal efficiency with the previous method. So the way we do that is still eta equal to Vt divided by h, right? Settle down with vertical velocity. Now we just need to calculate what is the time here, right? We're not going to give it indefinite amount of time. So time here is just the length of the duct divided by the flue gas flow rate or the flue gas velocity. Right? The flue gas always have a horizontal velocity of, let's say, u here. Okay, so under this situation, the time is just the distance divided by the velocity, right? And then we know that the efficiency is VH multiplied by L divided by U. Okay, so again, this V here is for a single size. It's for a particle with a single size, let's say dp, right? So if you have particles with 2 different sizes, 3 different sizes, or n different sizes, you can use the same method here, right? You have 2 different sizes. You can plug in the settling velocity with this concentration, right? Have n different sizes. You can also use that in this way. So basically this V here, let's say we assume that particles have a single size of dp, we can equate or the gravity equal to 3 pi mu dp divided by c multiplied by v, right? So what we can get is eta equal to dp squared rho p g cl divided by 18 mu hu. Okay. So this C here is not concentration, right? You know that the C here is the Cunningham factor. Okay. So basically, if we have n different sizes, we can plug in. We can just plug in this V here. That's different. We can separate that into different terms, right? And then if it's continuous, we can do the same. So following the previous method, right? So this is for a horizontal duct. I think it's still quite straightforward, right? It's similar to the settling chamber. The equation is also quite simple. So what about we have a tilted duct? Okay, so this is also something people will use in the particle removal devices. Right, the duct is not always going to be laid flat on the ground. So sometimes they maybe have to get elevated to a certain height there. So basically, we can use this tilted duct to transport the flue gas, right? Let's say that the flue gas goes in this way, right? It still has a length of h, length of L, height of h, right? The particles have a higher concentration here, maybe lower concentration here. So under this situation, how do we calculate the removal efficiency, right? So we can still use the same method, except that now we can do a force analysis, and then basically separating the gravity into two different directions, right? I think this is something you learn from physics, right? We can always separate the force into several directions. So basically, if we want to separate it into the direction that's perpendicular to the duct and also along the flow of the flue gas, right? Then we can separate that into two directions. And now if we consider the settling of the particles will just settle onto the base plate of the duct. So if theoretically, the force that's dragging these particles to settle down or getting removed, it's just this force here. It's just this force here, right? So this force tries to drag the particles to the base plate and then further get removed, okay? So we know that this force is basically mg cosine theta, right? So based on the mg cosine theta, we can calculate the settling velocity that's along this direction, that's perpendicular to the duct, right? So the way we do that is just equating mg cosine theta with the drag force. That's 3 pi mu dp divided by c multiplied by vr, right? Or we can just use the v here, mainly because the flue gas or the ambient environment doesn't have a vertical velocity. Okay, so this v here is just the settling velocity. Okay, so we know that the v is equal to mg cosine theta divided by 3 pi mu p divided by c. Okay, this is a settling velocity. So basically, we can still use this equation, right? It's just we need to plug in different terms. We need to plug in different a different value of the drag force, right? So now we have the settling velocity getting solved. But right here, if you notice here, the time of the particles that's spent in the duct is also different, right? Because although the particles will follow the flow, but there's also a force that's trying to pull the particle down, right? That's the other direction, basically the other factor of the drag force. And we know that this factor is mg sine theta. So let's say if the flow velocity is 0, then the particles will just free fall. It's going to settle in this way, right? This force tries to balance with the drag force that's created by the flow. So basically, the time of the particles that's spent in this duct is also different. It will become longer compared to a horizontal duct. So we know that for a horizontal duct, the time is just L divided by U, right? But for a tilted duct, this time is different, mainly because there's a force that's trying to drag the particles down in this way, right? So the way we solve that is still by equating the drag force with the external force on the particle, basically mg sine theta equal to Fd, which is 3 pi mu dp divided by c multiplied by Vr. So now we have to consider this relative velocity here, okay? Because we know the flow has a velocity. So previously the flow doesn't have a velocity on the direction that's perpendicular to the duct, and now the flow has a external velocity, right? So with this equation, we can calculate what is the relative velocity between the particle and the flow. So this relative velocity is mg sine theta divided by 3 pi mu dp divided by c, okay? And the actual velocity of the particle, or the VP, is basically U minus VR, right? So from this equation, we were solving the relative velocity of the particle and the flow. And to calculate what is the actual velocity of the particles, we have to consider the velocity of the flue gas. So that is U. That's why we have to use U minus VR. Okay, so that's going to be U minus mg sine theta divided by 3 pi mu dp divided by c. Okay, so with this actual particle velocity, we can calculate what is the time of the particles that's spent in this tilted duct. So time is just L divided by Vp. All right, which is L divided by U minus mg sine theta divided by 3 pi mu dp divided by c. Okay, so now we can calculate the particle removal efficiency, which is Vt divided by h. We know that the V is this term. That is the velocity that's perpendicular to the duct, right? And the time is the actual time that the particles spend in the duct. Okay, so we have basically dp squared, or let's just do it this way. dp squared rho pg c cosine theta divided by 18 mu h multiplied by L u minus dp squared rho pg c sine theta divided by 18 mu. Okay, so try to go through these equations after the class. Okay, so I know that there are a lot of symbols, but this is basically the general idea of how we solve for the removal efficiency of a duct. Okay, so basically this is the efficiency of the particle removal in this tilted duct. Okay, so if you compare with the horizontal duct, I'll just write out the equation. So what we had was here, right? So this equation. So we had dp squared rho pg cl divided by 18 mu hu. So let's compare these two terms. All right, so we see that basically, let's say we take the ratio. So this is tilted, this is horizontal, right? Then eta tilted divided by eta horizontal. We can cancel quite a lot of terms here, right? So dp squared rho pgc got canceled, right? The L can get canceled. 18 mu h get canceled. So basically, we just have cosine theta multiplied by u, or just put u here, and then u minus dp squared rho pg c sine theta divided by 18 mu. Okay, so this is a ratio between these two removal efficiencies. So which one is bigger? Which one is smaller? Right. So by directly looking at this ratio here, we can just consider a situation, right? So let's say theta is equal to 10 degrees, okay? So because the theta is larger than 0, so the cosine theta is going to be below 0, right? And then if we look at this denominator here, and because the sine theta is larger than 0, so basically the denominator is going to be below u. It's going to be smaller than u. Okay, so basically both the numerator and denominator become smaller. So it's going to be difficult to tell. Okay, so actually if you use your Excel or basically use the computer to plot out what is the efficiency of a tilted duct, you can find out that it's going to have a maximum angle. It's going to have an optimized angle where you're going to have the highest efficiency. Okay, so it really depends on the theta here for an actual tilted duct here. So here we're having a situation that's for tilted duct, but the flow is pointing upwards, right? So we can also have the situation of a duct that's pointing downwards. We have a velocity, we have angle here. So you can use this as an example in your homework problem. So this is going to be one of your homework problems. And then try to look at how the efficiency changed with this situation, okay? So it's going to be quite different compared to the situation we talked here. All right, so we mentioned that it's difficult to tell how the efficiency compares to a horizontal duct, but for this one, there's a definite answer. It's going to be either larger or smaller. Okay. All right, so finally, for the horizontal duct, we can make some summaries here. Okay, so for the settling chamber, for this set of settling chamber or the gravitational settling, the efficiency is quite difficult to solve. It's just basically VT divided by H, right? It's just when we have tilted duct or when we have a particles with different sizes, we just need to plug in with different parameters. But let's have a question. So is the settling chamber an efficient way to remove the particles? Okay, so let's consider the efficiency here. So if it's efficient enough, probably we don't need to build all of those other particle remove or particle control devices. We can just build duct to remove the particles. But it turns out that this is very inefficient. Okay, let's just write no here. So a simple example is, let's consider 10 micrometer particles. So we always talk about PM10 or basically PM 2.5. Let's talk about the larger particles. For PM10 particles, we can calculate the settling velocity is around 3.1 multiplied by 10 to the negative 3 meter per second. Okay. In order to let these particles to settle down 1 meter, let's say let the particles to settle down 1 meter. So we can calculate the time, which is 1 divided by V, right? And that turns out to be around 300 seconds. Okay, that's around 5 minutes. Okay, so let's assume that the flue gas, actually the flue gas coming out of the coal-fired power plant is at a relatively large flow rate, somewhere around 10 meters per second. Okay, so if it's 10 meters per second, to remove or to let these 10 micrometer particles to settle down for 1 meter, we have to build a duct that's basically 300 multiplied by 10, which is 3,000 meters. Okay, 3 kilometers. So that's very unrealistic, right? So we cannot build this long of a duct to just remove particle, 10 micrometer particle for just 1 meter. So that's why we have to employ other different types of particle remove devices, right? So the particle settling in the duct is just a passive method, right? So we're not using this method to specifically remove the particles, but since we have to build these ducts, so just let the particles settle down so that we can get rid of some of the larger particles, right? So that's all for this class. I know that there are quite many equations that we went through, so try to go through the the recording as well. So you will have 1 or 2 homework problems that's related to this settling chamber. All right. So let me know if you have any questions. Thank you.